Another application concerns log linear relations, and here we are going to suppose that I have two variables x and y, and they are related by this equation: y is equal to capital A multiplied by x raised to the power little a. And here I know that x, y and a are positive. And if that is the case, if x, y and a are positive, that means I can now actually take logs on both sides. So if I take logs on both sides, I can have log y. Now this log is to any base. We are not necessarily thinking of the base little e. So we are thinking of log as logarithm to any base. And if that is the case, I can take logs on both sides. So I will have log y is equal to log a plus little a log x. I can easily write that because of the fact that x, y and capital A are positive. So if I take a look at this, here we have log y as a linear function of log x, and this is what we call a log linear relationship between x and y. So this is a log linear relation between x and y. Basically, log x and log y are related to each other in a linear fashion. That's what I mean by a log linear relation. So it's a log linear relation between x and y. So if I'm talking about a log linear relation between x and y, that just means in this case we have linear relationship between log x and log y. And in most economic models, we are actually going to go from this to this with natural logarithms. So in most economic models, we move from y is equal to a multiplied by x raised to the power little a to ln y is equal to ln a plus a ln x. So we move from, let's say if I call this 1 and I call this 2. So in most economic models, we move from 1 to 2 with natural logarithms. And let us suppose we have two positive variables. Keeping all this in mind, or against this backdrop, let us suppose we have two positive variables x and y, and we know that, let's say we have a table wherein we see the relation between these two positive variables. If I make a new table and I take ln x and ln y, so let's say we have a table wherein I have the relation between these two positive variables, and that relation is set out in that table. If I take up ln x and ln y and make a new table for that relation between ln x and ln y, and I plot those results in a coordinate system, and when I plot those results, I have ln x and ln y. So ln x is measured on the horizontal axis, ln y is measured on the vertical axis. If I plot the results in a coordinate system in this manner, and if the resulting points that I get to a very good approximation, if they are all on a straight line, that just means that ln x and ln y are related to each other in a linear fashion. And if ln x and ln y are related to each other in a linear fashion, that just means, as in approximately, that just means that the relationship between x and y will be approximately of this form: y is equal to a multiplied by x raised to the power a. And what I just said, I'll just take up a question wherein we can understand this. So let's say I have this table and I have a relationship between x and y. and this is the relationship. So x is, let us say, 28,316, 49,412, 77,906, 122,085. This is x, 28,316, 49,412, 77,906, 122,085. And then I have y, it is 664, then it's 1028, then it's 1501, and then I have 2010. Now let's say x denotes total expenditure, total consumption expenditure, and y denotes consumption expenditure on healthcare. So here, let's say x denotes total consumption expenditure y denotes consumption expenditure on healthcare. Consumption expenditure on healthcare. Now, if this is the case, and we have, let's say we have different consumption expenditure groups. So this is one consumption expenditure group, this is another consumption expenditure group, this is another consumption expenditure group, and this is another consumption expenditure group. So we have 4 different consumption expenditure groups with us, and corresponding to these we have the expenditure on healthcare. So this is the table wherein we have the relation between x and y, both are positive variables. What we now do is we make a new table, and first of all we take up ln x and ln y, and we take a table wherein we see the relation between ln x and ln y. So for that I write ln x and I write ln y. So with the help of calculator I take up ln x. Ln x here is 10.25, then we have 10.81, then we have 11.26, and then we have 11.71. 10.25, 10.81, 11.26 and 11.71. If I take up ln y, that means I first take up ln 664, so that's going to be 6.50. Then I take up ln 1028, that is 6.94. Then ln 1501, so it's going to be 7.31. Then ln 2010, which is 7.61. So I have this table for the relation between ln x and ln y. If I plot this data in a coordinate system wherein ln x and ln y are measured along the two axes, so ln x is measured along the horizontal axis, ln y is measured along the vertical axis, and if I plot this data in that coordinate system, I get this diagram. I get this, and we see here that if we roughly fit a straight line through the point pairs, we see that it's if I just try to join those points in this diagram, if I just try to fit a line through the point pairs in the diagram, I see that I get an approximately straight line, and it's a very good approximation so I can see that if I have the straight line, it kind of gives a very good approximation to all the numbers in this table. And that means clearly ln x and ln y are related to each other in a linear fashion. So if I have to think of the equation of that line, the equation of that line will have this form: ln y is equal to ln a plus little a ln x. And if I want to find out this equation, or let's say I want to find out, let's say I don't want to find out this equation, but I want to construct a formula for y as a function of x. But I know that ln y and ln x are related to each other in a linear fashion, in an approximate manner, to a very good approximation. So I can write this equation, and I can see that this equation will approximately hold true. Also, in this case, I have ln x and ln y given here. And if I use these extreme points, but in this case, the slope is little a for that straight line. And if I use these extreme points, so let's say I use these extreme points and this. And I think of the slope of the straight line. So that would be, if you can recall, it's y2 minus y1 divided by x2 minus x1. So y2 minus y1 would be, in this case, y2 minus y1 would be 7.61 minus 6.50 divided by 11.71 minus 10.25. And this will be equal to 1.11 divided by, okay, so this will be 1.46. Now this turns out to be approximately equal to 0.76, and that means our slope is 0.76. Now which slope am I talking about? I'm talking about the slope here. So the slope here is approximately equal to 0.76. Let's say I require the line to obviously pass through this last point, which is 11.71, and then it's 7.61, this one. So that means we can think of ln y, which is equal to, so I can just put those numbers here and take up what is ln a. So if I see ln y, it's 7.61 is equal to ln a plus little a I know is 0.76, ln x I know is 11.71. Now this gives us ln a is equal to 7.61 minus 0.76 multiplied by 11.71. Now this is going to turn out to be minus 1.2896. So if ln a is minus 1.2896, what is ln a? ln a is nothing but the power to which e has to be raised in order to get capital E. That means in this case a is equal to e raised to the power minus 1.2896. This is ln a. This is the power to which e has to be raised in order to get capital E. So if we calculate this with the help of the calculator, this will approximately turn out to be 0.275. That means, so this, I know that when I write ln y is equal to ln a plus little a ln x, that means ln y and ln x are related to each other in a linear fashion. That means y and x are related to each other in this way. Y is equal to a multiplied by x raised to the power a. So here I can write what a is. It is 0.275 x raised to the power little a, which is 0.76. So that means we get this relation between y and x. So from this diagram, not that diagram, from that table, we have actually constructed an empirical formula for y as a function of x. Just by looking at this table, we have constructed an empirical formula for y as a function of x. The way we go about is that we first take up ln x and ln y, we make a table, we plot those in a in a coordinate system, and when we do that, we see that the resulting diagram gives us an approximate straight line. That means ln x and ln y are related to each other in this linear fashion, and from that we can deduce that y and x are related to each other in this manner, that y is equal to a multiplied by x raised to the power little a. And now we take up this. So now let's say y is an exponential function. Please keep this in mind, that this is different from what I just talked about. So when I say y is an exponential function, let us say y is equal to a multiplied by little a raised to the power x. Keep in mind the fact that a and capital A are positive. Now this is different from what we earlier considered, that was y is equal to a multiplied by x raised to the power a. So that's not an exponential function. This is an exponential function wherein y is equal to capital A multiplied by little a raised to the power x. If I take log on each side, that gives me log y is equal to log a plus x log little a. Now this is clearly possible because capital A and capital A and little a, these are positive numbers and these are positive. So I can easily write log y is equal to log a plus x log a. Now in this case we see that log y is a linear function of x, and here what I mean to say here is that if I have a coordinate system wherein we have x on the horizontal axis, we have a linear scale on the horizontal axis, and we have a log y scale along the vertical axis. So that's going to give us a straight line, and the slope of that straight line will be log little a. What I'm trying to say here is that this is not a log linear relation. This is the case wherein log y is a linear function of x. And if I say that log y is a linear function of x, that means if I have a coordinate system, so if I want to think of this equation, if I want to plot this equation in a coordinate system, what I will see is that if I have an ordinary linear scale on the horizontal axis, and if I have a log y scale along the vertical axis, this will actually give us a straight line. Given this equation, it will give us a straight line with the slope log little a. So this is not a log linear relation. Log linear relation is when you have ln y and ln x along the vertical and horizontal axis respectively. Here we have x on the horizontal axis and log y, or we can also think of ln y on the vertical axis. So there's a little bit, not little bit, there's a lot of difference between the two cases. In this case, when I talk about an exponential function, y as an exponential function, that is related to the case wherein we have ln y or log y on the vertical axis and just x or the ordinary linear scale on the horizontal axis. This is different from a log linear relation wherein we have ln x on the horizontal axis or log x on the horizontal axis, and we have ln y or log y on the vertical axis.